Greetings and welcome to Lecture 7.1. We're starting to learn about systems of linear equations. For example, here's a setup. We have two companies that offer internet access to their customers. Company A charges $10 a month plus $3 for every hour of internet connection. Company B charges $18 a month plus $1 for every hour of internet connection. What we can do is we can compare these monthly charges of the two companies, and the equations that we form will be called a system of equations. Here's that system. So the first company, what's going to happen is your total bill is going to be $3 for every hour plus the $10 a month charge. So y equals 3x plus 10, that's company A. Y equals x plus 18, so it's $1 for every hour, so there's an implied 1 in front of the x. So those two equations together are called a system. So what I can do is I can fill in the table. And I just filled in the first 10 hours of use. So let's see. For 0 hours, I plug it into my equation. 3x plus 10, the cost will be 10. For 1 hour, I plug it in, it will be 13. For 2 hours, I can plug it into the equation, it will get me 16, so on and so forth, all the way down to 10 hours. Likewise, I used 0 hours all the way to 10 hours in the company B's cost, and I can get 18, 19, 20, 21, and you can see the hour difference, the dollar is that next hour of use. And then I can compare both companies in a graph. So at first, company A is less expensive until it hits this point right there, and then it becomes more expensive. Likewise, company B is actually more expensive until it hits this point, and then it becomes a less expensive plan. So that's what's called a system of equations, and we're going to get a little bit more in depth about how to solve these. So two linear equations considered at the same time, that is very important, at the same time, is called a system of linear equations. Both equations contain two variables, and of course, they have graphs that are straight lines. The following are examples of system of linear equations. So here's one system, x plus y equals 3, and 3x plus 4y equals 2. Another system of equations might look something like y equals 2x plus 1, y equals 3x plus 2. And even a third example might be 2x minus y equals 1, 3x minus 2y equals 6. Do they have to have whole numbers? No, they can have decimals, they can have fractions. I just chose whole numbers to show you what a couple of systems of equations might look like. The solution set to a linear system of equations is all the ordered pairs that are solutions not just to one equation, not just to the other equation, but to both the equations. This ordered pair is the point of intersection. That's where the two lines cross, if indeed they do cross. So there are actually three possibilities of solution. So the three solutions are, one is that there is one solution. The lines cross in one place. So it has one solution. Right there is the point of intersection, so therefore it has one solution. Another possibility is that the lines are actually parallel, and if they are parallel, they never cross, therefore the system is inconsistent. It has no solution. The third option are the lines are exactly the same line. The lines coincide. That means they sit on top of one another. The equations are dependent. That means that every single point on the line is a solution to the system. Therefore, there are infinitely many solutions. Let's solve the following system by graphing it. What I do recommend that if you are going to try and do these problems, number one, you can use graph paper. That's always the best. Number two, if you don't use graph paper, use a ruler. Making the points equal distance and very precise will help you find the solution when you're graphing it and have to look at your solution visually. So I highly recommend graph paper or just invest in a little ruler. So here we have a system, x plus y equals 4 and x minus y equals negative 2. So I'm going to plot both of the lines just by selecting some points, and I plot the line. The blue line is x minus y equals negative 2. The red line is x plus y equals 4. And at this very point, if I'm very careful, at 1 and then up 3, 1, 2, 3, let's see, yeah. At that point, that is my point of intersection. What that means is that 1, 3 is the solution to both of the equations, to the whole entire system. So I'm just going to check to see if that's true. When x equals 1 and y equals 3, the equation x plus y equals 4 becomes 1 plus 3 equals 4, and yes, indeed, 4 equals 4. Likewise, when x is 1 and y is 3, the equation x minus y equals negative 2. Well, 1 minus 3, does it equal negative 2? Negative 2 does equal negative 2. So the point 1, 3 satisfies both equations. So there's a way that we can solve by graphing, solve linear systems by graphing. The first step, graph the first equation. The second step might seem obvious, but graph the second equation, but it must be on the same set of axes used for the first equation. If you have one graph over here and one graph over here, no, you're not going to really find your solution very well, but if it's on the same graph, you can see where they intersect or not intersect, or if they're the same exact line. Then the third step is you want to read the coordinates of your point of intersection of the two graphs, if there is one. And then the fourth is you want to do this check, because if you're looking at it visually, it might be off a little bit if your graph is not plotted well or drawn very well. So you do want to check your solutions to make sure indeed are you reading the graph correctly. Okay, let's see another system. We have x plus 2y equals 8, 2x minus 3y equals 2. So again, I'm going to just choose some points and plot each line individually. And I have plotted those. So my green line is x plus 2y equals 8. My red line is 2x minus 3y equals 2. And if I was very careful with my plotting, I can see that 4, 2 is my point of intersection. So my last step is to take that point, plug it into both equations, and see if indeed it holds true for both equations. What I mean by holds true is I plug in x equals 4 and y equals 2. X is now 4, y is 2, so 4 plus 2 times 2, 4 plus 4 is 8. 8 equals 8. That is a solution. 8 always equals 8, and therefore it is a true statement. Plug it into the second one, the second equation. So 2x minus 3y equals 2 will become 2 times 4 minus 3 times 2 equals 2. We're not sure yet if it does equal 2. 8 minus 6, does it equal 2? Yes, 2 equals 2. Therefore, 8, 2 satisfies both equations, and therefore it's a solution to the whole system. So here's a little problem that might be a little bit more complex. We are still going to plot these separately. So y equals 2x minus 3, and our second line is x equals 3. Now the y equals 2x minus 3 is a typical line that we're used to working with. We choose an x, we solve for y, choose another x, we solve for y, and we can plot it. Remember that when x equals a number, that is a vertical line. So I'm going to be plotting a vertical line that goes through the x-axis at 3. When I do that, here's my graph. I plot my y equals 2x plus 3 by choosing a couple points in plotting. And then my second line, I have x equals 3, which is a vertical line. And you can see where it crosses is at 3, 3. So 3, 3. Is it a solution to the system? So I'm going to plug it in to check. 2 times 3 is 6, minus 3 is 3, and y is 3, so 3 equals 3. And when it's 3, 3, we can write this equation as x plus 0y equals 3. So it doesn't matter what I plug into y, this is just going to be a 0. So when x is 3, it equals 3. And that's how we know that it is indeed a solution to the system. So let's go ahead and solve this system by graphing. We have y equals x minus 2, and we have y equals x plus 1. When I graph both of these lines, they are actually parallel lines. They will never cross. And because of that, they're inconsistent and there is no solution. It's an empty set solution. So you can either say no solution or empty set because they're parallel lines. Here's a clue as to how you can tell that they're parallel without even graphing it. If you remember, the number that's in front of x, and right now it's an implied 1, is the slope. And if each line, when it is in this the slope-intercept format, if both of the slope is exactly the same, then the lines are parallel. So the slope of the first equation is 1, and the slope of the second equation is 1. Well, because they have the same exact slope, they're always going up or going down at the same rate of speed. So they're never going to cross. So that's a way you can tell even without graphing if they're parallel lines or not. Let's try one more example of a system of equations. We have 2x plus y equals 4, and we have 4x plus 2y equals 8. And when I plot these lines, they turn out to be the same exact line. So I'm not too sure if you can see it, but there is my green line and my red line, and they're sitting on top of one another. Therefore, they're dependent lines. They're coexistent amongst themselves, and therefore every single point on the line is a solution to the system. So the last two examples were very particular special examples that you might run into. Okay, now it's your turn. Go ahead and complete this class problem and bring it into class our next class session. Solve by graphing the following system of equations: x plus y equals 3 and 1/2 x minus y equals 1. So until next time, be seeing you.